Welcome to Copilot Podcasts. Did you know that 2/3 of distant galaxies seem to be spinning in the same direction? It's a cosmic dance that's baffling astronomers. Today, we're diving into the mathematical wizardry of Bishopian modular spinors and how they might explain the very shape of our universe.
And it's absolutely fascinating how this connects to some really fundamental mathematics that's been puzzling scientists for over a century.
Before we get into the deep stuff, help us understand what exactly are spinors.
Well, you know how we all learnt about vectors in school? Spinors are like the weird cousins of vectors. They're mathematical objects that describe rotation in a really special way.
Special how?
Here's the thing, you need to rotate a spinor twice to get back to where you started. It's like they can detect whether something has been rotated 360 degrees versus 720 degrees.
That sounds counterintuitive.
Right? And according to recent research, these spinors might be key to understanding something called modular fluctuations in cosmology.
Modular fluctuations? That's a mouthful.
Yeah, so according to a paper by Aalsma and Bach from March 2025, these fluctuations are like tiny quantum ripples in the fabric of space-time.
And how does this connect to galaxies?
Well, that's where things get really interesting. Recent observations from the James Webb Space Telescope have shown something unexpected about galaxy rotation.
Tell me more about these observations.
According to research published in March 2025, about 2/3 of observed galaxies rotate clockwise, while only 1/3 rotate counterclockwise.
Wait, shouldn't it be roughly equal in a random universe?
Exactly. That's what makes this so puzzling. It suggests there might be some underlying structure we don't understand yet.
And this is where Bishopian modular spinors come in?
Yes, because they might help explain these large-scale patterns we're seeing. The math suggests that quantum gravity fluctuations could affect the structure of space itself.
But how do we even study something like that?
Well, researchers are using something called causal diamonds. These are regions of space-time that are causally connected.
Sounds complex.
It is, but here's what's fascinating. These quantum fluctuations seem to follow a specific pattern, what's called the VZ scaling.
VZ scaling?
Named after Valindi and Zurek. They found that these fluctuations are actually enhanced from the Planck scale, the smallest possible scale in physics.
And this enhancement affects galaxy formation?
That's what the math suggests. These quantum effects might actually influence the way matter distributes itself on galactic scales.
That's mind-blowing. Quantum effects influencing entire galaxies.
And it gets even more interesting when we look at spiral galaxies specifically.
What about them?
Recent studies show that spiral arms follow very specific mathematical patterns. They're usually represented by logarithmic spirals with slowly changing pitch angles.
And these patterns relate to spinors somehow?
Yes, because spinors might help explain why these patterns emerge in the first place. They're like the DNA of rotational motion in the universe.
That's a beautiful analogy.
You know what's really interesting? The famous mathematician Michael Atiyah once said that spinors are like the square root of geometry.
The square root of geometry? What did he mean by that?
Just like understanding the square root of -1 took centuries, he suggested that fully understanding spinors might take just as long.
But we're making progress, right?
Absolutely. The James Webb Space Telescope is giving us unprecedented data about galaxy formation and structure.
What are some of the most surprising findings?
Well, one puzzling observation is that there's a sharp decline in the Milky Way's rotation curve at about 15 to 20 kiloparsecs from the center.
And that's unexpected?
Very. It suggests that our galaxy's dark matter halo might be much less massive than we thought.
How does this connect to the spinor mathematics we were discussing?
The spinor framework might help explain these unexpected patterns in galactic rotation and structure.
It's amazing how abstract mathematics can reveal such concrete things about our universe.
That's the beauty of it. These mathematical structures aren't just abstract concepts, they seem to be deeply embedded in the fabric of reality.
What are the implications for our understanding of the universe?
Well, if these theories are correct, it might mean that the universe has some inherent rotational structure we hadn't recognized before.
Could this change our models of galaxy formation?
Absolutely. Some researchers even suggest that the universe itself might have been born rotating.
That's a pretty radical idea.
It is, and it would mean our current theories about the cosmos are incomplete.
What's next in this field of research?
Next-generation surveys like the Simons Observatory and CMB-S4 will provide even more precise measurements.
And these will help confirm or reject these theories?
Exactly. They'll help us understand if these patterns we're seeing are fundamental to the universe or if there's something else going on.
It's fascinating how mathematics can predict things we later observe in nature.
That's what Eugene Wigner called the unreasonable effectiveness of mathematics in natural sciences.
As we wrap up, what's the big takeaway for our listeners?
I think it's that the universe might be even more interconnected than we imagined, from quantum fluctuations all the way up to galactic structures.
And spinors are helping us understand these connections.
Exactly. They're like a mathematical key unlocking the secrets of cosmic structure.
Well, that brings us to the end of today's episode of Copilot Podcasts. It's mind-bending to think that abstract mathematics might explain why galaxies spin the way they do.
And remember, every time you look up at the night sky, you're seeing these mathematical patterns in action.
Thanks for joining us on this journey through the mathematics of cosmic structure. Until next time, keep looking up and maybe brush up on your spinor algebra while you're at it.